Welcome to this short lecture on blockchain decentralization, where we'll unpack why these systems matter and how they're built. Over the next slides, I'll guide you through the key ideas, trade-offs, and real-world examples, using diagrams to make the technical parts easier to follow. Think of this as a practical tour from basic value propositions to the engineering choices that shape decentralized networks. This slide contrasts the old intermediary model with decentralized systems and highlights three core benefits: lowering censorship risk, reducing fees, and enabling peer-to-peer value transfer. The graphic shows how cryptographic proofs and economic incentives replace gatekeepers, making records immutable and transactions trustless, which reduces rent-seeking and opens direct global exchange without centralized middlemen. Consensus is the algorithmic glue that turns a loose network into a single, verifiable ledger and prevents double spend. The slide compares proof of work and proof of stake as ways to convert economic cost into voting power, and emphasizes that decentralization here means no central referee. The math and incentives together ensure agreement and defend the network's integrity. Different node types play distinct roles in network resilience. Full nodes store the complete history, light nodes check rules more efficiently, and miners or validators propose new blocks. The diagram illustrates how these roles interlock to create permissionless replication and redundancy, so the system resists single points of control and gains strength as more independent participants join. Three core technical enablers make blockchain tamper-evident and verifiable. Hash pointers that link blocks so any change is immediately detectable. Digital signatures that bind transactions to owners without revealing private keys, and Merkle trees that allow lightweight verification of many transactions. Together, they let strangers maintain a transparent, incorruptible ledger without a central authority. The blockchain trilemma frames decentralization as an engineering balance among decentralization, security, and scalability, where optimizing all three at once is difficult. The graphic shows centralizing forces like bigger blocks and points to sharding and layer, two solutions as approaches aimed at relaxing the trade-off. The takeaway is that decentralization requires active design choices, not passive expectations. Decentralization can erode over time through economies of scale. Proof of work tends to favor industrial mining and capital concentration, while proof of stake risks wealth compounding and validator dominance. The slide highlights continuous defense strategies such as client diversity, encouraging home nodes, and governance minimization to preserve decentralization against these natural centralizing pressures. Decentralized lending pools illustrate both automation benefits and new risks. Smart contract code replaces traditional underwriting and custody, enabling global access to a pooled collateral market. The illustration also warns that oracles and admin keys can reintroduce single points of failure, so protocol design must balance openness with careful controls to avoid centralization in practice. DAOs are presented as internet-native cooperatives that use token-weighted voting and code-enforced quorum rules to coordinate action. While they distribute control across geographies, the slide flags governance challenges like low voter turnout and whale dominance, which can undermine true decentralization unless participation and incentive design are actively managed. Permissioned blockchain examples from Walmart and De Beers show how partial decentralization can deliver tangible business value. Shared, permissioned ledgers improve supply chain traceability and diamond provenance, enabling faster recalls and reducing counterfeit goods. The cases demonstrate that targeted decentralization can reduce fraud and operational risk while respecting commercial confidentiality. For scaling, the slide contrasts roll-ups and shard chains. Roll-ups offload computation and batch transactions off-chain, while anchoring proofs to the main chain, boosting throughput without sacrificing verification, whereas shard chains parallelize work across independent shards, coordinated by a beacon chain. Both approaches aim to scale, while avoiding single operator reliance and preserving core decentralization properties. Finally, Decentralization should be viewed as a spectrum rather than a binary state, shaped by ongoing design choices like code upgrades, hardware distribution, and token ownership. The diagram emphasizes that network control is a living requirement. Architects must continuously decide how decentralized they want a system to be and manage trade-offs as the network evolves.